Hello, Brian. Can you hear me?
Yes, I can.
Okay, perfect. I think we're all set. And as always, we'll start on time. I would like to thank you, the people that is already connected and the people that will be hearing in the recordings. And for us, it's a pleasure and an honor to have Brian Fairchild with us today. Besides the curriculum and besides that Brian works with the University of Georgia and he's a teacher and he's a professor and the extension poultry scientific. I believe that Brian is has been providing a lot of value in his research and his passion in the poultry industry, not just in US or Latin America, worldwide. So we're very honored to have you, Brian, here. And I think that our main goal in poetry school is to share knowledge. And I think that we really are aligned with your values to keep pushing forward. And we really appreciate your time, Brian. So today we have the title Poultry House Evaluation for Hot Weather. I think that you guys are gonna enjoy it. And besides the information, my main thinking is that how to apply it, how to go to our farms and to our companies and put this knowledge to practice. So, Brian, the time is yours, and let's go. Thank you, Brian.
Okay, thank you. Okay, so I was asked to talk a little bit about hot weather poultry house evaluation. And so when we talk about this, we want to try to make sure that we have the right tools to make sure that we're doing this properly, make sure that we're getting good measurements. It really does require the right set of tools with the right accuracy. So the first thing that we typically recommend is the use of a kestrel. This is a nice little instrument to have. I carry mine in my computer bag, and it goes with me everywhere I go. And this particular model, the Kestrel 3000, is the one we typically recommend because it will measure wind speed, and it gives us both a minimum. I mean, you could look at maximum wind speed, you could look at average wind speed, or you could even just look at real-time measurements. But we typically just look at averages because otherwise, if you're measuring on the just looking at the wind speed reading, it does never stabilizes. It's just constantly moving. And with the average, after you wait for 2 or 3 minutes to get a good average, you can it's a very stable reading. And typically we don't wait 2 or 3 minutes. It's usually about 30 to 45 seconds. This instrument will also do both temperature and relative humidity. And so like I said, it's a nice little quick check instrument to have with you. I use mine a lot when I'm out and about doing farm visits and evaluations. Now, one of the things the meter does have that we don't recommend using is it will calculate a heat index and wind chill. But these are based off of human. These instruments were really originated for campers and hikers to use outdoors. And we've used them in poultry houses for our poultry house environmental checks. And we just got to keep in mind that this heat index and the wind chill function that it talks about in the instruction manual and is available to you, it doesn't mean anything for the chickens. And so I don't think I've ever even used this function on my latest Kestrel 3000 that I have. And so I would not recommend, and you should not be using that function. Now, one of the nice things about this Kestrel line is that it has a replaceable impeller. So you could just pop these impellers out, you just push it through. And whenever these things start making a little bit of noise, there's a little bearing right here. And when those instruments start to rattle a little bit, that bearing might be going bad, and it could affect the accuracy of your readings. And so you can replace these impellers for about $15 to $20 a piece rather than having to buy a whole new instrument. And that's a nice feature for this particular brand. Another option is a Bluetooth anemometer made by Weatherflow here. And I've been using it now for about 2, maybe 3 years, I guess. And it'll connect Bluetooth to my phone. And one of the nice things about this is if I'm out doing multiple measurements in different houses, I can store the information in my phone. So I don't have to have a pen and paper right there at that minute to write everything down. I just need to keep in mind which order I took the readings at. Of course, it has its own little app that you download to your smartphone, and it'll give you all these readings. You can store the data, and we can also click for more data, and it'll even show us all of this information right here. So it's a pretty neat little instrument here. It still gives you temperature. It'll still do relative humidity, and it'll also do the airspeed, and especially that average that we're looking for right there. Another tool that I like to carry with me whenever I'm out visiting farms doing assessments is going to be the non-contact tachometer. Basically, this shoots a little beam of light. It's usually a red laser that kind of shoots through, and you can measure that. It'll do a blade count, and these run about $250. There's another brand out there too, made by Cybertech. It's much cheaper. It's about $30. And it seems to work pretty good. I most usually end up using the Monarch since I have that one first, and just keep using it. But anyway, both work pretty well the same. You just point it at the fan, and it'll do a reading. I think I have a video of that here in just a second. And what that's going to do is give you a blade count, and then you have to divide by the number of blades to get your RPM. The other tool that I carry with me all the time is going to be our magnehelic gauge. It's going to be a measure of measuring the static pressure. And I like this mechanical magnehelic gauge. It's the Dwyer model 2000-00, and it sells for around $100. And the reason you need to pay attention to the model number is because of the scale. We measure static pressure in inches of water column typically. And so really, we want that scale to be between 0 and 0.25. And, you might get into some layer houses that are pulling more than 0.25, and you could get a different model if you need to. But for most broiler, breeder, pullet houses, turkey houses, this is the range that we're going to be in. So that would be the model that would give you the 0 to 0.25. And then we've also got the digital meter options as well. And there's even an electronic one that will connect Bluetooth to the phone and have a software app that you can download and use that as well. I typically tend to stick with these because they give me more stable readings quicker. And so it's quicker for me to get a stable reading using the magnehelic gauge than it is to use some of these digital meters, because these numbers just keep jumping around when I'm trying to do a measurement, and you just have to kind of pick which one you saw the most. Another tool that we like to recommend people to have whenever they're evaluating the poultry house, especially for poultry house detecting leaks in poultry houses, is we like to make sure we've got a fogger that can create some smoke. In this case, we're using an insect fogger, and there's a couple of different brands out there. They run off of a little tank of propane that you hook into it. And what we do is we put in mineral oil, and it'll create this nice white smoke. It smells pretty good too. And we'll go down the side of the walls and just smoke the outside of these walls, have somebody on the inside with the fan running, and you look for that air to be pulled in through cracks and leaks that you need to seal up. Another one that you need is a thermal camera, not a temperature gun. Temperature guns were great back in the day. That's when we really needed to use them. That's all we had, and they did a wonderful job. But the problem is they only do one single point in measurement. With a thermal camera, you can get a nice overview of the house, like we show here in this picture, and each pixel becomes a data point. And so these gives us thousands of data points, whereas with this one, you get one data point for everywhere where you point the thermometer at. So we're seeing more and more people, and these give us a bigger picture. It's a very visual aid too. This is only going to give you numbers. This will give you these pictures. You can really see those warm spots and cold spots when you're evaluating this. The thing is this technology, gosh, I think when we bought our first camera, which is probably about 18 years ago now, was when we got our first camera. We used that for about maybe 10 years, maybe 12 before we upgraded to a new camera. But our first camera ran about $30,000 by the time we bought it. Now these cameras have come down in price, and obviously it's all devoted to resolution. The more resolution you want, the more expensive the camera is going to be. So let's take look at a few of our choices here. So there's several different cameras that are out there on the market. We've tested and utilized the FLIR quite a bit in our work. It also happens to be the brand of our more expensive camera as well. So that's why we've stuck with them, because of the software that we use to analyze the data in the thermal images. But this particular unit right here, this is the FLIR 1 Pro LT, and it runs for about $280. It's got what we consider to be a pretty low resolution. It's 80 by 60, which is going to give you 4,800 measurements. And it's got a fairly good accuracy of plus or minus 2 degrees Fahrenheit. That's not bad for a $280 instrument. But I really don't recommend this one. Really, the one I would be pushing people to get if they're going to buy one for the phone is going to be the FLIR 1 Pro. This one runs about $370. I just checked it this morning to see what the current prices were on the internet. It has a higher resolution, so it's 160 by 120, which gives us 19,200 measurements. Accuracy is the same. It's just that when you look at those pictures and you see the detail, it's much clearer. So here's an example. Here's that low quality image, the 80 by 60, compared to the 160 by 120. And so you see the differences that you can pick up. I'm going to do that again one more time so you can compare the two. Here's the lower resolution, and here's the higher resolution. One thing to keep in mind is these cameras are also light sensitive as well. A true thermal camera, when you buy a standalone camera that doesn't plug into your phone, those really don't depend on light in the house, light intensity. But these cameras will typically do a better job when the lights are a little brighter than when we've got the light intensity turned down really low, because it's using a combination of the thermal camera, the FLIR 1 Pro, and it also uses your camera as well to kind of merge the two images together to get this quality image here that we have. So here is a medium definition. This is a standalone camera now. We're not plugging this into the phone. So this is 240 by 320 pixels, which gives us 76,800 measurements. And you see the leakage along the top of the wall right here around this inlet. You can see a little bit of leakage right here, how it's got a little bit of cool floors. And so when we start looking at some of these different units here, you've got the FLIR 1 Pro LT 250, the FLIR 1 Pro, which is if I was going to buy one for my phone, that's the one I'm going to get. And that is the one I carry with me in my computer bag. And then you can get into like a mid-level series, which is going to run somewhere, depending on the value, the brand, as well as the resolution. It's going to be somewhere between $5,000 to $10,000. And it's going to give you that resolution of 240 by 320 pixels. Then you go into your high definition cameras. And this is the one when you see a lot of our pictures, this is what we typically use for presentations, for our newsletters that go out, things like that that you might have seen from us in the past. We're going to use our higher resolution camera. Plus, we're going to use this for our research as well because it gives us 307,200 measurements for each picture that we have here. So when we start doing the data analysis, we can really get some good numbers out of this. So here we're looking at our low resolution, the LT versus the high resolution, and you just see the difference between them. Unfortunately, as with most things in life, you get what you pay for. So to really get that high image quality, high resolution, it costs. And so this camera currently is running around $27,000 to $30,000 for this particular model, the T640, which actually, I think the T640 has actually been discontinued now, and they've replaced it with a 800 series model. There might be one, a 500 series model too that's available. Okay, so those were the tools. These are the things that I like to have on hand. So like I mentioned already, some of the things that I carry with me, pretty much keep in my car when I'm driving around is going to be the Kestrel 3000. I'm going to have my Magna Helix gauge. I'm going to have the FLIR 1 Pro. I'm going to have those usually with me at all times. The tachometer, I usually don't keep that with me all the time. And it really depends on what I'm going to do that day or whether or not I'm going to be needing that. But we'll talk a little bit about more of that as we get through this presentation. So one of the things we got to do is we want to make sure that the controller is providing good quality data, because everything that the controller is trying to do, it's basing it off of the information it's getting from these sensors. So is the sensor reading correctly? Is the temperature sensor reading correctly? Is the static pressure sensor reading correctly? So we want to make sure that we test these. And so to evaluate these temperature sensors, one of the quick ways to do this is to go in and open up the tunnel doors or your tunnel curtain, whichever you have, turn on some fans. Then you're going to wait about 15 minutes or so to give the house time to equilibrate. Usually I'd probably do these when there's no birds in the house, because that way you'll get probably a more uniform temperature in the house. Whereas if you've got birds, it's going to tend to want to warm up as the air moves down the house as it removes heat from the birds. Then we go in there and take a look at our individual sensors. And what we're looking for is they should be reading pretty close. We're wanting them to be a little more than 1 degree difference between them. And so it's not unusual to walk in there and see them all within a half a degree or better. But boy, if it's a 1 degree or better difference doing this test, then you're definitely going to want to check the sensor and make sure it's reading correctly. So to check these sensors, we need to use a high accuracy thermometer, which pretty much means that for most temperature guns that a lot of people buy, they're not going to be accurate enough to do this calibration check and test. So what we do is you might want to go to a higher accuracy thermometer. And the reason we're using this food thermometer is, and I'll show you in just a second, is because it can be put down in water. And so this is a good example of one that has got good accuracy. It's plus or minus 0.5 degrees Fahrenheit. And what we're going to do, another piece of equipment we need is going to be a bucket. And we're going to fill that 5-gallon bucket approximately half full of water. And we're going to let that sit there around. You're going to need to sit for a while, let it come up to room temperature. It's not necessary to do that, but if you really like to be at that room temperature when you're doing your measurements, because that's where your system's going to be measuring at, and your sensors are going to be measuring at, typically is within that range. So after we let our water warm up a little bit to room temperature, we go in there, we take a reading with the high accurate thermometer, and then we take the temperature sensor and we just dip the little probe down into the water and wait for it to register. Now, we're going to need someone there at the controller to take note of the water temperature whenever we put the sensor in. And we're going to do that for each one of the sensors. And like I said earlier, if it's a degree or more difference, we're going to recalibrate the sensor. We're going to repeat these for all the different sensors. So most of the time, these sensors are reading accurately. That is one good thing, is that the temperature sensors that we've been using in the industry, they typically do very well. They have a good longevity, and they don't really fail on a regular basis. So a lot of times, I said 9 times out of 10, the sensors are reading accurately. Well, sometimes for that 1 time out of 10 when they're not, we find that there's been calibration factors that were entered into the controller when they weren't needed. And so there's a couple of reasons why that might have happened. Maybe the calibration procedure they used caused some differences and they weren't getting an accurate reading. Or it's highly likely that the tool they were using to calibrate the controller sensor was actually less accurate than the control sensor itself. So that's why we want to make sure that we're using a good, accurate thermometer when we're doing that water temperature measurement to make sure that we're getting that good. Now, why do we use water? Why don't we just take an air temperature measurement? Well, it depends on how much air movement's going on in the house, where you're at. But those sensors that air temperature can change and fluctuate. And so water temperature tends to be a little bit more stable. It doesn't change as quickly. And so that's why we would be using the waters for a stable reading that we can take for both the temperature sensor as well as the high accurate thermometer. The other thing to keep in mind that I see a lot of times is when I go in there and outside temperature, let's just say it's a nice sunny day and it's running about 85, maybe 80 degrees. And it's not that uncomfortable, but your temperature sensors, outside temperature sensors, reading 96 degrees. And the reason is that the sensor's okay. It's not out of calibration, but the solar radiation that's hitting that sensor is throwing off the reading. And so to obtain an accurate outside temperature, our temperature sensors should be housed within a radiation shield, so the sun cannot hit that temperature probe directly. The other sensor that we're going to want to check to make sure it is reading correctly is going to be this controller static pressure temperature. The static pressure sensor accuracy. And so here we can see, for example, we can just use the controller and we see that we're running some fans. We're getting a 0.12 inches of water column pressure in the house. But really what we want to do is make sure that the test is conducted when there's no or minimal wind outside the house. Because when that wind's blowing, it's going to create pressures on the house and the inlets, the fans, and it's going to cause it's going to create some issues trying to get accurate static pressure readings. And so let me go back. I'm going to play this video for you again here. And you can just see what the wind's doing right here as it's blowing, how it's moving back and forth. So you really don't know what the right reading is when the wind's blowing like that. So we want to make sure that our airspeed's our pressure sensors being collected on a relatively calm day. First, we want to make sure assuming it's a calm day, we're going to make sure the pressure sensor is properly zeroed. So one of the easy ways to do that is just to open up the box here and pop off these tubes and turn off all the fans and just look at your controller. And it should be 0.00. If it's not, we just need to go in and use the calibration setting right here in the software on the controller to re-zero the sensor. Next, we're going to check the pressure sensor accuracy with the fans running. And so we're going to turn on some fans, we're going to get our pressure up to maybe a 0.1, 0.15 inches. So, it's going to take maybe 1 or 2 fans with the inlets closed. to get a fan. Depends on how tight your house is, depends on the size of the fan. But you want to get about a 0.1 to 0.15 pressure. And then we're going to go in and we're going to use our magnehelic gauge, which is going to be taken in pretty much the same general area as where our tube is for the static pressure sensor in the controller. So we want to do that reading in the same general area. If there's a difference in the pressure between the controller and the magnehelic gauge of more than 0.01, we want to make sure that first the tubes are properly connected to the sensor in the controller. You're going to want to look for any type of punctures that might, like mice or other rodents might have chewed into the tubing. And then, of course, we want to make sure the tubing's not blocked. And that, as you can see, like in this particular example, where darkling beetles had got into the tubing and would have been restricting that air, the pressure detection inside that tube and just block it. So we make sure those tubes are not got any holes. Make sure they're open. They're not blocked in any way with debris or bugs. The other way we could do this is we could actually take the tubing and we could connect it directly to our magnehelic gauge and get a reading. And we can compare this reading right back to the static pressure sensor to see if they're reading the same. If there's still a difference after you've done your general magnehelic gauge, and then you go in there and you hook it up to you take the tubes off of the static pressure sensor in the house and you connect it to your magnehelic gauge, then if you still see that difference, then it could be that the controller is high static pressure is needs to be adjusted. This is rare that this is needed, but if it requires more than a 0.02 inch adjustment, you might want to think about replacing that sensor. But again, you can try to adjust it out, see if it holds it. But just be aware that once it gets a little bit over 0.02, typically that's not normal variation. There's something wrong. One more thing I want to point out on these magnehelic gauges. When you're using these, you got to keep in mind that there's 2 ports. It's the same thing with the digital pressure meters gauges that we talked about earlier. They've got 2 ports. One is going to be a high pressure and one's going to be a low pressure. So in this particular instance, we are standing inside the controller room and we have the tube going through the door into the house. And so we've got the pressure, we have the tube on the low pressure port to take our reading. And then that room where we're standing at is going to be the high pressure. If I was inside the house and I was going to run my tube outside through an inlet, then I would be putting it on the low pressure. No, I'm sorry. I'd be putting it on the high pressure and I'd run that tube outside the house where the high pressure is. So it's easy to put this on the wrong port, but you can tell pretty quickly that you've done it wrong because that needle is going to it'll never move off of 0. And so if you're trying to take a measurement and it won't rise up, odds are you've got the tubing on the wrong port. Next thing is checking our tunnel fan condition. One of the things we're going to look at is our shutters. Love to see them nice and clean, just like this all the time. But we want to make sure that, especially with horizontal shutters like this, that the dust that collects on there is cleaned off routinely because it can add weight to the shutters, which makes it more difficult for the fans to get them open. This can increase that pressure that the fans create a restriction and increase the pressure that the fans are working against to try to pull the air out of the house. And this tends to be more of a problem in houses that have got interior fogging nozzles, because as that moisture collects, it'll cause that dust and debris to build up on these shutters and just requires a little bit more frequent cleaning to keep them there. The other thing we want to do is make sure that the screens are clean. We want to make sure that get all this feathers and dust and debris out of the screens so we don't have any restrictions, because these dirty screens can create a back pressure And we've measured it as a 0.05 or higher before, depending on how much this screen is blocked. So the dirty shutters plus the dirty screens, that could add up to be a 0.1 inches of pressure that these fans are having to work against. And that can mean a lot when we're starting to look at the amount of air that these fans are going to be moving. Decrease it, several thousand CFM, which is going to lower our airspeed. In this particular example, this 15% reduction is going to lower the airspeed as much as 100 feet per minute. So we got our shutters all good. Now we want to take a look at the belts. And the belts, as you can tell on this particular pulley, if you've not looked at this before, this is a worn belt. It's riding too low into the pulley, which is going to cause the fan to spin more slowly. So we want that belt to be near the top of the pulley. You should be able to look at from the side of the pulley and see the top of the belt right above the pulley. If it's riding down inside the pulley like this, that belt has gotten worn, it's settled down into the pulley, and we're not turning the fan as fast as it could be turned. The lower that belt rides, the slower the fan's going to spin, and the lower the amount of air moved by that fan. So that's one visual way to look at this. Another way to look at and evaluate your fan and your belt condition is to use the laser tachometer that we mentioned earlier. So we take our laser tachometer. This is our video I was thinking of earlier. And we point that at the fans there. We get our blade count. And so it's basically just told us that is our blade count. Then we're going to take that blade count and we're going to divide it by the number of blades on the fan. This particular fan has got 4 blades. And that gives us 453 RPM, rotations per minute. Now we take that 453 and we're going to compare it to what it should be. How do we find that out? Well, we go back to the lab tests. That's why we strongly recommend that when you're purchasing fans and trying to choose a fan for your poultry house, that you get a fan that's been tested by a third party, such as Best Labs here, so we can get these numbers. And we're going to look at the RPMs here and what it should be moving. And we see it should be like around 511 RPMs. We were at 453. So now we do our math and we calculate our percent reduction, multiply it times 100, and we can see that that fan is 11%, it's spinning 11% slower than it should be if it was actually properly maintained. If that RPM is 5 to 10% below the rated fan speed, then we need to be thinking about replacing those belts. Go ahead and replace them. After we replace that belt and the fan speed's still lower than expected, then you really need to look at those pulleys and make sure and check for those signs of wear. Make sure the pulley's not gotten too worn. Because again, like I mentioned, that belt should be riding up in the pulley. And you can see here in this particular case, it is down below the pulley now. It's riding inside the pulley. And the other thing is, as these pulleys get worn, they can get this shiny little mirror-like polished look to them, which makes them a little bit more prone to slippage. That's also a good indication of pulley wear as well. So one of the quick ways, I usually use a tachometer. Doesn't take that long to go around there and actually get a number. But if you left your tachometer in your office or batteries are dead, you don't have batteries with you or something, then one thing you could do is just go into the house, get the controller, and basically what we're going to do is turn on each of these fans and write down the static pressure. So you're going to close everything up tight, tunnel doors closed, end wall doors closed, sidewall inlets closed, and we're going to measure the static pressure when we turn on that one tunnel fan. And we're going to repeat that procedure for every single fan. Write these numbers down, and we can see right here which fans might be having a little bit of an issue. These actually, there was a typo on that slide. I didn't see that earlier. It should be a 0.09. But we definitely see that fans 1 and 2, which are probably the fans that come on first and run the most, have got the most wear in those fans, probably the belts and pulleys, and it's slowed it down almost 20%. These two fans, just a 1 point difference here, can cost us up to 10% a slower air movement. So again, that's just a quick and dirty way of looking at the fans, looking at trying to decide which fan needs to be looked at. You can go around with your tachometer and get a real number reading with that and compare that back to the Best Labs fan test report for that particular fan. So that's why I always think it's a great idea whenever people buy fans to go ahead and download those files, save them to your computer, maybe print off a hard copy and stick in a notebook somewhere so that you'll have them when you need them. Evaluating the house tightness. Basically, we want these fans to come in. We want our air to come in through the evaporative cooling pads and through the tunnel inlet, not in through these curtains. It's very difficult to cool birds and provide a uniform environment in tunnel houses that have a lot of leakage. So one of the easiest ways to quantify the house tightness is to use the Poultry 411 app. So basically, what we want to do is, in a perfect world, we would turn on 1 CFM per square foot of floor space. So if I had a 20,000 square foot house, let's just say it was 40 feet wide by 500 feet long, and it's pretty easy in those size houses because I just need to turn on either 2 36s or I turn on 1 48-inch fan, and that'll give us roughly 20,000 CFM. That's 1 CFM per square foot. But with all these different house sizes we're getting, and we got these different fan sizes now that are capable of moving 21, 23, 25, 27,000 CFM, we needed a way to be able to calculate house tightness easier. And so this calculator takes into account those differences. And so what we got to do is plug in all the numbers and it'll calculate this for us. So when you go in and you click on the little calculator button here, it'll take you to the next screen. And our current version of the app has got 5 calculators. The one we're going to focus on today is going to be the Poultry House Leakage Calculator. So we're going to click on that. It'll take you to the next screen here. And for our example, we're going to use a 50 by 500 foot house. So that's 25,000 square feet. We're going to use 1 tunnel fan that's moving about 23,000 CFM. And we measured a static pressure with everything closed up tight. We measured a pressure of 0.05 inches of water column. Now, the fan that you choose to use is important too. I would not use the fan that comes on first. That's the one that runs the most. It's going to have the most wear and tear on the belts and the pulleys. So you want to use your best fan. And so try to choose that best fan when you're doing these house tightness tests. And that'll get you closest to your tested airspeed that or tested air movement that the fan's supposed to do. So we're going to take our information for this example. We're going to plug it into the calculator. So 550, 23,000 CFM, 0.05 inches. We hit calculate. And it gives us this information over here. So it basically tells us that we have 27 square feet of total house leakage in this house. That's approximately 1.08 square feet per 1,000 square foot of floor space. This is a loose house. It is not, this house could stand, there's room for a lot of improvement on this house. So we want to make sure that we get in there, we get the house tight. Let's say we go in there, we find out that, well, the end wall doors were loose. We tighten them up. We tighten up the tunnel door. And we go through and make sure all the inlets are closing tightly. Maybe we have to foam a few cracks around the doors or something like that that's letting air leak in. But let's say we do a good job, we get this static pressure increased. So our rule of thumb when we're doing this is that this slide might be out of place, but remember this for later. I'm sorry, this slide's out of place. But a rule of thumb we need to keep in mind is that when we're operating our tunnel ventilation at maximum capacity, every single fan's running, basically 350 CFM of air is going to enter through every square foot of pad opening. So approximately 1,000 CFM, like in our current example, is going to enter through every square foot of opening in that house. That's what that was telling us. So I'm hoping that puts this on perspective for you. 300 CFMs coming in through every square foot. And in our example, we had a little over 18 square feet of leakage in that house. That's a lot of air. So just think about that as you do these measurements and try to put that in perspective. So we come back, we've done our leakage area. We know that we've got that 29,000 and it comes out to be the 26.9 square foot leakage in that house. We go in, we do all those corrections I just mentioned earlier, and we get a static pressure of 0.25. We did a good job. We increase that back up there, or this could just be a brand new house. Either way, we do the calculation and we find out that we have got a really good house tightness here on this particular scale. Still says we got a little bit of room for improvement. And one of the areas I'd always look for when I'm doing this tightness test is going to be around the tunnel doors or around the in-wall doors. But the other part that could be leaking is it could be pulling some air in through the shutters of the fans that are not operating as well. So that could be another source of leakage. But anyway, done a good job here. We got this house tighter, and you can see that it really reduced that level of leakage per 1,000 square feet. So we've got much less air entering in through the cracks. So this is all good. Now we know that we've got leakage in the house. How do we find the leakage in the house? Well, that's where we start using that insect fogger that I showed you earlier, one of the tools that's nice to have around. Now, obviously, I don't carry this with me all the time. So when I'm going to a farm, usually I got to know ahead of time what the problems are, and I kind of decide which tools to take with me. Or sometimes I'll go visit a farm and I'm like, we need to come back and really smoke this house and see what's going on. But in this particular case, we're going to be using this fogger. You can see Mike here, he's fogging the outside of the house. I'm actually collecting the video here for him. So we got somebody else inside that's got the fans on, and they're marking the areas where we're seeing some leakage with either some chalk or maybe some flagging tape or something like that, so we'll know where we're tightening up at. So here we're checking that curtain. It's looking for any type of leakage. Over here, we're going to smoke that sidewall and try to look for some leakage along there as well. And so right now he's smoking down there around the bottom of near the stem wall. But a lot of times we'll go up and down just like that. And if there's any leakage along that wall, it's going to pull it in. If we see that the inlets aren't closed correctly, it'll pull it in. So walk around the exterior of the house and with the insect fogger, and you can visualize where that leakage is by looking for the smoke is coming in. Another way to do this is we could use our thermal camera. If you got the FLIR one, you can start looking for these hot air leakage here. You see where this hot air is up here at the top of the curtains coming in. You see a little hot spot right there. It's right moving right down. You see these warmer birds right up here near the stem wall. But it's not only a problem in curtain-sided houses. It can also be in houses with poor sidewall tightness as well, even in totally enclosed houses. So here's the north wall. It looks pretty good if I just look at that. But if I go look at the south wall, we can see there is a lot of heat coming through there. You can see the difference in the bird heat along those two walls. So obviously some room there to tighten up those walls and keep that air out of there and coming in and heating things up. Okay, so the next thing we want to do is we want to evaluate the static pressure with all the tunnel fans operating. So ideally, as with this tightness test, we're going to try to do this on our new houses on a calm day. And I really think, me and Mike are really pushing this to be done on new houses before we get started at the beginning, so that you have a baseline. That way, you know what you started with, and over time, you can evaluate how well that house is holding up. And if there's something that's really changing quickly, you need to try to figure out where it's at. But it's a good way to find that baseline to evaluate the status of the tunnel ventilation system in the future. So we're going to open up our tunnel doors here. So for this particular test, and we're going to open the doors up all the way, roughly around 45 degrees. We're going to turn on all the tunnel fans, which should be in good condition, good belts, good pulleys, good clean shutters. We're going to measure and record the static pressure. When we measure that static pressure, where should we be at? And ideally, we're going to be down closer near the fans. Usually the static pressure is going to be right here in the control room, and there'll be a tube right here at the middle of the house. But we got to keep in mind that static pressure is going to be higher at the fan end than it will be right here at the middle of the house. If we've got air deflectors in the house, if the house ceiling's a little high and we put air deflectors in, then there will be even more difference between the midpoint and the fan end of the house, because each one of those deflectors adds resistance that the fans are working against. And of course, the length of the house as well as the airspeed will make a difference as well. So we want to measure that true static. We want to measure the true total pressure that the fans are working against. So in order to do that, we want to be measuring back here near the fans. And so a lot of times what we're going to do is run our static pressure sensor through the inlet close to the fans back here. So we're going to choose one of those inlets here, probably within one or two, maybe three inlets of the fans to do our measurements. What should you expect to see when you do this pressure test? It's going to depend on your airspeed. The more airspeed you have, the higher the static pressure will be. Just think of it as drawing fluid through a straw. The harder you pull, the higher the pressure is going to be inside the straw as you pull that drink or that liquid through the straw. So we want to, we kind of have these ranges here. This is based on a lot of research over several summers to come up with these numbers. But they do give us a nice expectation in terms of what we should expect at these different airspeeds. If you check the pressure a few months later on that new house and the pressure is higher, then it might indicate that the pads need cleaning, or the tunnel door might not be fully opening, or your tunnel curtain might not be opening up all the way correctly. That's and we see that a lot with tunnel curtains, about how they don't rise up or get raised up all the way out of the way. And so we'll have some of it hanging down, which is restricting that tunnel inlet a little bit. If the static pressure decreases, it could indicate that the tunnel fans need some maintenance. And even though it's rare, it might indicate that you've got some leakage that's occurred already. So you need one of the things that we typically see is stretching of the strings that pull those inlets closed. And so you may need to check those to make sure that the sidewall inlets are fully closed. Next thing I want to check is going to be the evaporative cooling system. With all the fans operating, I want to take the Kestrel and I'm going to hold it up next to the pad here. And like we mentioned earlier, we should be getting approximately 350 feet per minute. So we're looking for something between 325 and 375. Whenever we do this, if it's less, then it could be a dirty pad. So if it's dirty, It could, it could be pads being dirty, or it could also be a fan maintenance issue as well. Dirty shutters that aren't opening up all the way, or fan belts, fan pulleys, everything we've already discussed. It could also mean that if it was lower, that the pad system was oversized, but that's something you could test at the beginning. When you do that initial airspeed check to look at your pressure, you can also check to see what your airspeed going through the pads are, just so you'll know. But hopefully people don't oversize those pads too much. Another reason why the pressure could be higher is if you've got insufficient pad area, or more likely, typically, we'll see high portions of the pad are restricted because they've gotten dirty. And so one of the things we can do is just take a bucket of water and you just splash it on one area pad. Sometimes we might do 2 or 3 splashes. Then we turn around and we're going to take our reading before, we can do it before and after, or you can just read a section next to that wasn't cleaned, and then measure the area that you did splash the water on to clean it. And that's really been a good way, especially when I'm on the farm and it's something that just kind of comes up unexpectedly. Everybody's got buckets around, so it's real easy to show them this test. But if there's more than a 50 feet per minute difference between these 2 readings, before and after, then you're going to need to do some cleaning on those pads. But if I know I'm going out to a farm, and I know that they're struggling with some airspeed, I really like to try to have a new pad with me. And what we'll do is we'll take out one of the old pads, put this new pad in, and then we do the same measurement. We measure over here and get the first measurement, then we measure where the new pad is, and it's a very good way of demonstrating to people how maybe how much their pads have deteriorated or how much they really need to be cleaned. So you can see here that there's almost a doubling of the airspeed of the new pad versus the old pad. Okay, of course, when it comes to hot weather, it's all about airspeed, airspeed, airspeed. So we want to make sure that we measure the airspeed accurately. And one thing that we've learned is that air velocity is going to vary significantly depending on where you measure it. So what we've done in the past, we've done a lot of tests with this where we've set up these 15 anemometers. This is 5 poles. And we've done this on dozens of farms. I've kind of lost count, so I need to go back and just actually count how many farms we've done these tests on. And so basically we'll put these sensors 2 feet off the floor, 2 feet between this sensor and that anemometer, 2 feet between this anemometer, and 2 feet off the ceiling. And then we space them evenly across the house. And of course, this will just be a mirror image of what we have over here. So we're measuring these samples continuously in all of these locations. It says 12, but it should be 15. Then we record these every minute, and we usually run somewhere a minimum of 15, somewhere between 15 and 30 minutes is when we're recording this data. And this is how we've learned all this stuff. Even in the best care that we've taken, measuring air velocity, just in the same location, we can see that the air velocity can change as much as plus or minus 25 feet per minute from minute to minute. So, it takes some time. That's why we do such long measurement periods in order to account for that little bit of variation that's going to occur. Here's an example of a house that we took the pads out of, and it's got 54-inch fans. We measured our average airspeed at around 800 feet per minute, and we can just see the variation in our measurements on all of those 15 points in the house. So we've got our high areas, which tend to be up near the ceiling, lower areas over near the sidewall, down towards the floor. So again, was it surprising to see differences or significant differences from floor to ceiling, as well as along the length of the house? So where is that ideal location? Because you're not going to go in there and set up 15 anemometers. We don't do that every time either. So when I go with my Kestrel and I'm going to go measure where I'm going to try to measure the air movement in this house, the airspeed, we're going to want to stand approximately 50 to 100 feet in front of the tunnel fans. So about 150, somewhere between 50 to 100 feet. So let's just say 75 feet. We don't want to be near any obstructions like a tunnel curtain. We don't be near a furnace. And ideally, we wouldn't be near a migration fence either. Then we're going to hold that sensor, just like Mike's showing right here. We're going to hold that sensor about directly out from us. That puts it about 4 to 5 feet off the floor for most people. And we want to measure approximately 5 to 10 feet from the sidewalls. So usually that puts us somewhere around this feed line right here. So a lot of times I'll just go and stand right around this feed line, or maybe just to the right over this water line, the outside water line here. And I do that on both sides of the house. So when we're measuring this air velocity, we want to make sure that we've got the airspeed meter in the proper position. We want to make sure that we're standing parallel with the direction of the wind. I don't want to be standing directly in the wind because it could bounce off of me and affect the reading of the Kestrel on the anemometer. So that's why you can see here he's standing parallel with the wind, kind of holding it to his side. Then we're going to hold it at arm's length, which is going to put us in that 4 to 5 foot range. We're going to turn the meter on and hold after it's been there for about 5 seconds, we turn that meter on and we take our average reading. Do this 2 or 3 times in a couple of different spots. I like to do it here at this line. I go to the house, do the other line on the other side of the house, and I average them together. Too often, I hear this all the time, people tend to take measurements in the center of the house. And that's just not what I really care about. That's where it's going to be the fastest. And that's wonderful that we have a good airspeed there. But I'm more concerned on how the birds are going to be cooled in the slower areas of the house. And so we really want to be measuring to try to get that average airspeed, which is why I'm going to tend to be closer to the sidewall in that 5 to 10 foot area that we just mentioned. So I know that this was pretty quick. I could have talked for at least another 30 minutes. But I understand people are busy, and listening to me for 45 minutes has probably been enough. So in summary, we have talked a little bit today about the tools and instruments that you got to need, that we would recommend having to do a proper and accurate poultry house assessment. We want to find these, test our house tightness, and using that house tightness calculator, locate those leaks using the smokers, and then we're going to fix them and then retest that house tightness again. We want to check our sensors. Hopefully you won't have to do the calibration procedure, but at least check those sensors and make sure they're reading at least 2 or 3 times a year. Then you want to do fan maintenance. That should be at least 2 times a year, if not more often. You're checking those fans, making sure they're running right, because it's absolutely critical to have those fans operating in optimal condition during hot weather. The evaporative cooling system does need to be cleaned routinely, and that's another whole presentation in itself on doing that properly. But we want to make sure we minimize the air restriction that might be created as we pull air through the pads. And we covered on some of the basics of measuring the airspeed, where to stand, how to stand, and what instruments to use to measure that. So with that, I hope you'll find this useful as you go back and take a look. I know we're in December right now, so it's not really hot weather, but time moves quickly. And so, now's the time to start doing a lot of these checks, thinking about this stuff before we get into hot weather, because this house tightness especially is really important when it comes to cold weather maintenance as well. Thank you.
Thank you very much, Brian, for your 60 minutes presentation. You say 45 minutes, but it was exactly 1 hour. So
Sorry.
we're very excited. No, well, fantastic. Yeah, like you say, we can spend as much time here getting all your knowledge. I have in the chat, if somebody else have another question, in your screen, there is a question and answer box. I have two questions here, Brian. The first
Okay.
one says from Babu N. What is the maximum ventilation for young broiler chicks at a hot weather? I think that maybe there is more data, but yeah,
Yeah.
that's the question. The
So
question, right?
I mean, honestly, we get that question a lot. People want to know, hey, what's the maximum ventilation? What can we put on those? And so again, boy, we could do another 45-minute talk on this, Rodolfo, but really what we look at is we call it the rule of thirds. So let's just say that we have a house with 12 fans, and we're going to divide that flock up into thirds. And it's just a quick, simple example. And let's say we're growing a smaller bird, depending on where you're at. Some people consider a 42-day bird relatively small, but we're going to grow a 42-day-old bird. So that's 6 weeks. So we're going to divide that up into thirds. You got 2 weeks, 2 weeks, and 2 weeks. So the first 2 weeks, you would only need to be using a maximum of 1/3 of your fans, which is
Okay.
going to typically, give you, I mean, it depends on the house, but it's going to be somewhere probably in that area of, I don't know, somewhere around 250, maybe to 350 feet per minute. It really depends on how the house is designed, what fans you have. But I would focus, if you're really worried about what your maximum air should be, it's going to be, I'd use the rule of thirds, in simplest way of explaining that right now.
Okay. Perfect. The another question that is in the chat is somebody that is asking for information if they can have more training in the US. So what I would recommend you is Gajendran from India.
Uh-huh.
So maybe to email you guys, and maybe you can offer your courses or your openings for more instant training. Okay?
Right. Well, Rodolfo, if you don't mind, I mean, I'm assuming, I know Rodolfo knows, our host here today for Poultry School. I know that he knows this, but we do offer 2 workshops every year. There's a cold weather workshop that we do in November,
Mhm.
and we do a hot weather workshop in April. And those are done every year. You can go to poultryventilation.com and you can register your email address there at the website, or we usually post this on our Facebook page that you see here. Whenever we have our programs and we announce the dates and registration information for our various
Yeah.
workshops, those will be available there as well. So, but if Ginger here wants to email me, I could put him on a list to make sure that we send that out as well. But that would be, I'm not sure here. I'm reading the question myself. It said something about taking 3 years of a poultry course in your
Yeah.
country. I don't know if that means come here for 3 years or what, but anyway, but we offer those workshops, which I think, it sounds kind of like I'm bragging in a way, but I really think these are good workshops. We provide a lot of good information on
Agree.
the principles behind it. We talk a little bit about operation, and we send you home with a lot of knowledge so you can go back and really assess your farms and operate them hopefully optimally in the future. So I would just recommend attending those workshops initially, just to kind of see if that answers a lot of your questions.
Okay, so Brian, if you can see the question box, there is another one for Uday, the last question.
So is there a
Uday,
maximum airspeed specification with respective to age, like maybe like by week wise, or age of birds by week,
mhm.
2-week-old birds, 4-week-old birds? Again, I'm going to kind of, it's so difficult to give everybody a specific answer because of the differences in house design, the differences in the number of fans you might have, the size of the fans you might have. So it's very difficult. So I'm going to fall back to what I mentioned on, for the first question about using the rule of thirds. And really, the first 4 weeks in hot weather, that's really the only time that's really, I kind of have to watch that airspeed. Once you get about 4 weeks and those birds are getting feathered very well, they're starting to fill up the floor space of the house and your bird density, your pounds per square foot is increasing. It's very difficult to chill birds in hot weather. And so I tend to be pretty aggressive when it comes to moving air over birds during hot weather because I want to keep those birds comfortable. I don't want their body temperature to increase. So again, I'm going to kind of refer you to the explanation that I just gave a few minutes ago about taking the flock, divide it up into thirds, and let's just say you've got 12 tunnel fans. Then that means you'd use 4 fans in the first 2 weeks. You'd use a maximum of 8 fans in your next through 4 weeks, and then use all your fans in those last 2 weeks, if needed, depending on the temperature and what the house conditions are telling you.
Okay, perfect. Sounds good. So I don't see any more questions in the question and answer box. So I would like to thank you everybody that put time for this live presentation. We're going to be sharing this presentation in our social media channels for a limited period of time. So we'll be announcing that in social media. So I just want to thank Brian for the time also and for sharing all this knowledge. Like I say, we really appreciate their passion and their willingness to share knowledge. So Brian, thank you very much, and to everybody the same. And see you soon in the next one.
Thank you. I
Okay,
enjoyed it.
thank you, Brian. Thank you, everybody. Bye bye. Take care. Bye.
Bye.